Hello, everyone. This is Vitaly Podzorov, Rutgers University. And today I would like to tell you about our recent very interesting observation of unconventional scaling of CW photoconductivity and photoluminescence in lead-halide perovskites. So as you know, in CW measurements, essentially you have a sample illuminated with a light of constant intensity, and you can measure the physical properties such as photocurrent and photoluminescence as a function of, for instance, intensity of incident light or wavelength or polarization. And it turns out even in these relatively simple measurements, one can see a very interesting behavior that reflects the photophysics and dynamics of the charge carriers in the sample. And that's what we're gonna talk about. Okay, so while we're thinking about these CW measurements in these materials, we have to keep in mind that these are normally non-excitonic materials, at least in terms of these properties, these CW properties. They are characterized with a very long carrier diffusion length, much greater than light penetration length. And also they're strong absorbers, at least in the visible range. So now let's look at this type of experiment in a conventional semiconductor. So you are measuring photoconductivity with contacts, and you are coming in with a constant light intensity, so G or F, the photoexcitation intensity or incident flux, or simply just light intensity, okay? And we're looking at the CW case. And let's plot photocurrent as a function of light intensity in this double log plot. So what do we see normally? Normally, initially, of course, you see a linear behavior, and that comes from this rate equation written here on the left, written for the steady state photocarrier density n, okay? So there is a source of carriers that generated with some quantum efficiency, and there is also a channel of photocarrier decay. In this case, the decay is dominated by carrier trapping. Tau is a carrier lifetime, which is limited by trapping, okay? Now, in steady state conditions, n is constant, and therefore this is equal to 0. And this gives you a linear relationship between the carrier density and the light intensity. So you have slope 1. Then as one increases the photoexcitation intensity, in a dominant majority of cases, you would see a square root behavior. Okay, so this slope here would be 1/2, and this is due to this famous so-called bimolecular or electron hole recombination regime. That's the channel that becomes dominant channel of the carrier decay, immediately leading to this square root dependence. Okay, what is PL doing in concurrent measurements? So PL is shown here. I mean, expected behavior of the PL in this upper plot. So PL in these conventional semiconductors originates from a radiative recombination of electrons and holes, and therefore the PL intensity, IPL, so this is IPL is the intensity, is proportional to the product of charge carrier concentration for electrons and holes. So basically it's proportional to n squared. And therefore in this regime, you expect to see a slope 2 parabolic behavior. And in the bimolecular recombination dominated regime, the PL should be linear with the light intensity. Okay, so that's the expected behavior from this conventional model. Now, what do we see in reality in perovskites? Well, first of all, in order to start answering this question, we need to know what happens with the charge carrier mobility in these materials. And the first reliable measurement of the intrinsic charge carrier mobility of the perovskites was performed in this paper that you can see here on top. It was done here by using Hall and photo-Hall effect measurements. Using the technique, which is a very nice high-resolution AC Hall technique that we have introduced in this paper, where the oscillating magnetic field is created by rotating assembly of permanent magnets. The reason we need the mobility is because we are experimentally looking at the photoconductivity, sigma PC. But photoconductivity is essentially a product of steady state carrier concentration N and the carrier mobility mu. And while in the experiment, we are looking at sigma PC, in theory, we are looking at these rate equations, and the rate equations are written for the photocarrier density N. And so in order to be able to compare the photoconductivity and our rate equations, we have to decouple this carrier concentration and the mobility in this in the photoconductivity. And so our measurements with the Hall effect show that that in, for instance, in large grain polycrystalline thin films, typical mobilities are of the order of 8, well, probably up to 10 centimeters squared per volt second, and it is light intensity independent. You can see it's kind of flat here in this range. In single crystals, this is the case of MAPB system, the mobility can be up to 60, and it is also intensity independent. Therefore, in this expression for the photoconductivity, mu can be treated as simply as a prefactor. So we can directly look at our rate equation results. Now, the main result actually in this slide is shown here. This is the photoconductivity as a function of light intensity measured in these two systems. These two are highly crystalline systems, and you can actually see that it follows exactly the bimolecular recombination regime, because the slope in both cases is exactly 1/2. Okay, so this power exponent is 1/2 in both cases, and that tells us that the trapping term is negligible in this case. So the whole thing here is dominated by the bimolecular recombination, leading to this nice square root behavior. Okay, when we do the same measurement in much more disordered sample, so this is the case of almost amorphous spin-coated thin film, MAPI thin film, we see that photoconductivity shown here with open symbols has slope 1. Okay, so that tells us that in this case, the dominant decay channel is the trapping, because there are so many traps here in the system that tau is very small, so this term is dominant, and that leads to the linear relationship between the photocarrier density and light intensity, and that explains why the PL measured at the same time is actually quadratic. So the slope for the PL here is 2, exactly 2. That is explainable by this concept that PL comes from the radiative recombination of electrons holes, and therefore should follow n squared, and therefore it follows g squared behavior in this case. Okay, so far everything is clear, and there are no surprises. But the surprise comes when you look at the CW, both CWPC and PL measured in the highly crystalline case. So this is an example of this MAPB, or methyl ammonium lead bromide system, single crystals. And in this system, while photoconductivity shown here shows the expected behavior, so there is a transition from linear to a square root regime, PL exhibits some surprises. So initially it goes as expected. So here at low excitation, it has a slope 2, so it's quadratic as expected. But then it undergoes this transition into this regime, which is very strange. In this regime, the PL has slope, or the exponent, 1.5. In other words, it's 3 seconds, and it's exactly 3 seconds, while the expected behavior should be slope 1. So this exponent 3 seconds is very robust. Here I give some examples. we observe it all over the place in different materials as long as they're highly crystalline. I mean, these lead-halide perovskites. You can see it in MIPB system here. You can see it in fully inorganic cesium perovskite. You see, every time you see this transition from slope 2 to slope 1.5. In ferromagnetic system here, in MIPI single crystals, again. The only time we don't see it is in highly disordered films. And here we see the quadratic behavior simply because we're not able to reach high enough intensity where there would be a transition to the next regime. So this is a very robust behavior, and that's what we're trying to explain. Now, in this paper here at the bottom, we came up with 3 possible models that can explain this beautiful power exponent of PL. First possibility is this direct and direct band gap structure, where the photocarriers pumped directly undergo very quick relaxation to the side indirect minimum. Second possibility is the case of highly asymmetric trapping, when, for instance, electrons are strongly trapped while holes are mobile. And finally, there's a third possibility in this model of carrier diffusion in the presence of bimolecular recombination and a strong surface recombination. And so we argue in this paper that the first 2 models are irrelevant, and actually what's at play is this model number 3, the C case, C panel here. And a couple of more details in this model. Basically, we assume that almost entire incident flux is absorbed at the very surface because the absorption length is so short. We consider the carrier diffusion with long diffusion length. And then basically in this regime, you just write down the diffusion relationship, where you have the diffusion term, you have the trapping term, you have the bimolecular recombination term. But what is turns out to be very important is to write down this boundary condition at the top surface, where you basically say that the net flux at the front surface of the sample consists of the incoming flux due to the incident light. And there is also a sort of a back flux. So the motion of the carriers here in the bulk consists of 2 fluxes, effectively. Flux, which is this D, diffusion into the depth. And also there is a sort of effective backflow of carriers towards the top surface, simply because surface, the trap dominated surface, works as a carrier sink, it's absorbing the carriers. And this process is characterized by this parameter S, which is called surface recombination velocity. Now, it turns out that we can solve this model analytically in the limit of high surface recombination velocity. And it immediately leads to these results when the photoconductivity follows a square root behavior, and the photoluminescence follows this behavior where this exponent is 3 seconds, exactly as observed in our experiment. Okay, so I wanted to conclude here by saying that, well, first step that was instrumental to all these measurements is the measurement of the intrinsic carrier mobility in perovskite that we have done in these papers by using this AC Hall method with rotating magnets. That was important. And then we were able to observe correlated flux scaling between the CW photoconductivity photoluminescence measurements in perovskites that are governed by long-range carrier diffusion, bimolecular recombination, and surface trapping. And actually, if you look at the ingredients that we put into this model, which are listed here, very short absorption length in these materials, very long carrier diffusion length, and strong surface trapping. Well, compared to the bulk, which is trap tolerant, where there are very few traps, these all are very famous features of perovskites. Okay, with this, I would like to thank the students and postdocs participated in this research. Also, our collaborators, Yuri Garstein, very nice theorist from UT Dallas, Xiaoyang Zhu, and we thank the NSF for financial supporting our work. And thank you very much for your attention.